So the example is something that it's example for illustration, not for solving something that you can't do otherwise. So it's a delta function potential. V of x is minus alpha delta of x with alpha positive. And the ground state energy is well known, is minus m alpha squared over 2h squared. You've solved this problem many times in 804. So trial wave function. Well, you know how it should look, but let's assume you don't, and you say, oh, it's some sort of Gaussian. So trial. It would be psi of x equal e to the minus x squared. While this would do, it's not a, you're going to work hard and you're not going to reap all the benefits of this calculation. So what you should do at this moment is put a constant here, minus beta squared x squared, and I'll put a minus 1/2. It's your trial wave function. You see, by this, you're going to get an expression. You calculate this number, and you're going to get a function of beta. Beta is not going to disappear. And therefore, you're going to know that the ground state energy is less than this function of beta. And then you can adjust beta to get the best bound. So beta is put as a parameter to begin with, and we hope to use it. So note that integral of psi squared dx, in this case, is equal to square root of pi over beta. So we have to calculate this whole functional. So this integral of psi star, well, I don't have to bother with psi star because it's real, h psi over psi psi. And what do we get? Well, the denominator is easy, so we get beta over square root of pi. And let me write the whole thing here. Dx, the psi, would have e to the minus 1/2 beta squared x squared minus h squared over 2m d second dx squared minus alpha delta of x and another wave function e to the minus 1/2 beta squared x squared. Okay, so you have to evaluate that, and that's the part that is not so much fun. For any integral that you have in 805, we believe that you can use Mathematica or Maple or MATLAB or whatever and do it. The only reason not to use any of these things is if you think you could not do the integral. But once you realize, oh, this is an integral I know how to do, don't waste time. Use any of those programs. Now, this part of the integral is kind of easy because the delta function just picks the value at 0. So this part of the integral gives you minus beta alpha over square root of pi. The other part of the integral, however, is a little more complicated. Believe it or not, it makes a big difference whether you take the two derivatives of this function or you integrate by parts. If you integrate by parts, you save a lot of work. So let me integrate by parts. This becomes plus beta over square root of h squared over 2m, integral dx of d dx of e to the minus 1/2 beta squared x squared squared. So you integrate by parts one of the ddx's, and then you have the other ddx, so it's the thing squared. And that's an easier integral to do. So we don't want to bother with this, but this whole thing then becomes minus beta over square root of pi alpha plus beta squared h squared over 4m. That's the whole answer. And that's the evaluation of this whole thing. So look what you get. You got a function of beta, indeed. So how does that function of beta look? It's 0 for beta equals 0. It's 0 for some other positive beta. It's going to look like this. So there's a point at which this function is going to have a minimum, and we should choose that point to get the best upper bound on the function. So our claim is that, following from the variational theorem that we've proven, is that the E ground state is less than or equal than the minimum value over beta of this beta squared h squared over 4m minus beta square root of pi alpha. So you minimize over beta, and it's still, the ground state energy must be a little smaller than that. Well, what do you get? You do this minimization gives beta equal 2m alpha over h squared square root of pi. It's a little messy, but not terrible. And you substitute, and you get that E ground state is less than or equal than m alpha squared over pi h squared. And to recognize it better, write it as 2 over pi times minus m alpha squared over 2h squared, which is the true ground state energy. So let's just make sure we understand what has happened. Here is the energy. Here is 0. Energy is just a vertical plot. Here is 0. The true ground state energy of this problem is this one. Let's call it EGS, is negative. And we got 2 over pi times that. 2 over pi is about 0.64. So the bound says that here is 0.64 EGS. So that's what the bound told you. The bound state energy must be lower than this quantity. We got close, not impressively close, but the function was not all that bad either.